All right. I think we can go ahead and get started. It looks like the counter has kind of leveled off. I want to welcome everyone to a new semester of VQMS. Thanks for sticking around. We have a very exciting semester ahead of us. A few announcements before we get started. We want to all thank Dean, who was one of our founding members here, who will take sort of a break for a year or so, and we want to welcome two new members, two new organizers of VQMS going forward. Zhenling from Wharton and Yufeng from Rochester, welcome. As usual, what hasn't changed is that we still are sticking to 1 hour presentations, right? Panelists, thank you very much for being here as well. Panelists, you can unmute yourselves and ask questions during the talk. Others, please use the Q&A feature to ask questions, and then we can ask the question for you, or if you want, you can stick around for the informal discussion that happens at the end of the talk for about 10-15 minutes, where you can be promoted to panelists and we can have a discussion. With that, that's all that's new and old. With that, we want to welcome Giovanni. Please go ahead. Thank you.
Thanks so much. Thanks, Luca, and to all the organizers, as well as the panelists who agreed to join. I'm going to present a paper that is co-authored with a few co-authors. We started this a few years ago when I was actually an intern at Microsoft, and the paper was dormant for a while, and we kind of resurrected it last year during the or maybe a year and a half ago during the pandemic. The topic of the paper is online search and product rankings. So the starting point for the project is that we know by now that product rankings matter a great deal in e-commerce, and Raluca has a great paper kind of documenting and quantifying these effects. And so a natural question, given this, is how can a platform optimize its rankings? So we're gonna, in this project, take the perspective of a platform. In particular, we're gonna look at Expedia ranking hotels for customers. And we're gonna ask, what is the best way to rank products or hotels with two potential objectives in mind. On the one hand, a platform could be focusing on the short-term revenues and profits. So we're going to think about static revenue and profits. I use revenue and profits interchangeably because broadly, Expedia takes a fixed commission out of sort of the booking revenues that are made. There's some variation across hotels, but it's not huge. And so we're going to think of the two sort of as equivalent in this case, and the cost of listing a hotel is very low, so essentially no cost for the platform. And on the other hand, we're going to think about a potential other objective, which is optimizing consumer surplus. This is the objective that a policymaker might have, but also a platform might be interested in maximizing this in the long run. When it faces competition from other potential entrants or other competitors, and therefore needs to sort of keep consumers happy to avoid losing. And so what we do in the paper is to propose a model of search and choice that has two key features. It's a tractable model in a way that I will describe in a second, and it's also microfounded, so it can be motivated by sort of standard assumptions on how consumers are searching over products. And so the model is going to feature two indices per good. So the key feature of the model is that each good is going to have two scores or two indices. Utility index, which is just the utility that you get, the standard utility you get upon consuming the product. And a search index, which broadly is sort of how salient the product is on the results page. Before the consumer searches the product, before the consumer learns more about it. And this structure is going to give us a very, very convenient closed form expressions for the two key things that we care about, which are profits and consumer surplus. Given this, we're going to use the model to study optimal rankings with, again, a focus on maximizing profits and maximizing consumer surplus. And we're going to develop algorithms that approximately, in a way that I will make precise, maximize either of these two objectives. And then we're going to apply this machinery to Expedia, to the Expedia kind of setting. So just very briefly, we don't have a lot of time, so I'm going to give a very, very incomplete sort of review of the literature, but just broadly, we sort of relate to the literature on search, theoretical literature that we leverage to motivate and to microfound our model, as well as the empirical search literature. So relative to the empirical search literature, which is very broad by now, and so here are just a few examples of papers, we focus on the optimality of ranking. So really, our key focus is to develop an algorithm to optimally rank products, and so this is sort of the way we see our paper as positioned relative to the to this literature. On the flip side, there is a literature on ranking optimization in computer science and operation research. And here, especially, there's a very recent paper in management science, this Direction et al. Paper. Our kind of contribution is to have a model that is a little bit more microfounded, and particularly that sort of has a microfoundation that matches the patterns that we observe in the data, and also to apply this to actual data, because a lot of this literature usually sort of illustrates the approach on synthetic data sets. And finally, we speak to the literature on platform design, because ultimately, sort of, we are suggesting and proposing a way to, design a feature of the platform, the rankings in this case, with a given objective in mind. So, without further ado, let me jump into the model, and I'm happy to take questions in just a couple of slides once I've laid out sort of the general framework. We're going to have a model where consumers are choosing between capital J goods and an outside option, which I'm going to label by 0. And as I sort of already hinted at, each good is going to be characterized by 2 scores or 2 indices. Utility score, which is, again, our usual utility enjoyment of consuming a good, which I'm going to assume is a function of observable attributes, X. So these are things that are observable to the econometrician, are in the data. Of things that are not in the data, CJU, so this is an unobserved quality, if you will, term that is not in the data, but that contributes to consumers' utility, and an idiosyncratic shock, epsilon ij, also not observed by the econometrician. The search score is going to be a function of, similarly, of observable attributes of unobserved things that are not in the data. The same idiosyncratic shock epsilon, so this is actually going to be key to our closed form solution. So the fact that the same shock shows up in both places, and I'll show you in a second how to think about microfounding this restriction. And on top of that, the search score is going to be allowed to depend on the rankings of the product. So a product that is ranked higher is going to be have all else equal a higher search score. Because it's more salient to the consumer. So again, in terms of interpretation, the search score is basically you can think of this as a measure of how salient a product is on the results page. So this is something that sort of the benefit that the consumer can hope to get from a product before clicking upon it. And so in terms of information, the consumer knows the search score for all products before search, and then needs to search and potentially pay a search cost in order to learn the utility score for any of the products. Given this, we're gonna posit that consumers follow the following search algorithm. So for now, I'm just gonna basically assume that this is how consumers behave, and in the next slide, I'm going to provide a micro foundation for this. If the utility of the outside good is higher than any of the search scores for the inside goods, the consumer just stops and chooses the outside option. So basically exits the market without even searching anything. If this doesn't happen, then the optimal sort of the way that we assume the consumer searches is to go down the list in decreasing order of the S scores of the search indices, and to stop whenever the highest utility that they have uncovered so far, which is this term here, exceeds the next best search score. So whenever the utility in hand that they have uncovered so far exceeds what they hope they can get from searching the next product, they stop. And once they stop, they choose the good that maximizes utility in the set of search products. So again, this is
Giovanni,
for now. Yeah,
sorry to interrupt. Conceptual question. If consumers knows this search score S already, which includes the epsilon, then in the search process, what exactly are they searching for in the function?
That's exactly sort of what I'm going to be talking about well, really the next slide, so I can answer this right away. So for now, I basically just kind of assume that at a high level that this is how consumers behave. So let me provide a few actually possible microfoundations for this behavior. So one is to assume that consumers are searching over the CJU term. So basically they know the X's, they know the epsilon, because again, this is actually one of the key restrictions that we want to maintain. And they search over sort of this unobserved quality. So think of it as consumers not really knowing, besides the X's, how good a given hotel is or a given product is, and searching over this sequentially. So if consumers do this, then we know by sort of seminal paper by Weitzman that the optimal search rule is going to be determined by search scores or reservation values. This is the terminology of Weitzman that solve these equations. Where essentially the net benefit of searching on the right-hand side is sort of equals the search cost CJ. And so given the structure, basically we can, so the Weitzman paper kind of tells us that the optimal rule involves ranking products by the search score, going down the list and stopping whenever the utility that they have uncovered exceeds the next best search score. To specifically motivate our functional form for the search score, which is the one down here at the bottom of the slide, we can make a couple of other assumptions. And so in particular, if we assume that consumers form expectations about CJU, given what they know about the product, the X's, in this way, so we're assuming a linear kind of expectation function. And if we assume that search costs are a function of rankings, which seems pretty normal, so pretty intuitive, the products that are ranked in better positions have lower search costs, then it can be shown, and we sort of go through the derivation in the paper, that the search index or reservation value in the Weitzman sort of framework will take this form here. So consumers will, the reservation value will be a function of what the consumers know about the product, the X's and the epsilon. Notice that the X is multiplied by not just the beta use and not just the utility that the consumers know they will get from the product, but also by the expectations that they form by this gamma term, because they form expectations about the unobserved, what they don't know, the CU based on the X's. And because search costs depend on rankings, this term F of R will also show up here. So again, products that are ranked in better positions will tend to have higher search scores. And so this is captured by the F of R term. So as you can see here, this is a special case of this general functional form here. In the special case, what I'm labeling here is CJS is just not there. It's just set to 0. And the beta S coefficient is just given by beta U plus gamma. So this is one possible microfoundation, but it turns out that this derivation is actually, or this argument actually goes through even if we sort of invert the order of, or the role of X and C. So we can also assume that consumers know the CJU for all products. So they know how much sort of, again, this quality term that is unobserved through the equilibrium, we can assume that consumers know that. And instead that we can assume that they are searching over the X's. So a similar argument would sort of then lead to this form under this informational assumption will lead to this functional form for the search score. Or we can also assume that consumers are searching over both CU and X. And this would be the functional form for the score in this case. So all of these are special cases, again, of this general form. For example, in this case, we just, for this latter one, we would just set beta S and CS to 0 and obtain this form for the index. So these are sort of possible microfoundations for the the algorithm, the search algorithm that we posit. And I just want to briefly mention that the idea of this double index model is actually more general. So before our specific parameterization for the search index, which we're going to maintain throughout the paper, this idea of sort of consumers using two indices per good, a utility index and a search index, is actually more general. And so this can be mapped sort of other search protocols, including simultaneous search models, such as the Stigler model, can be mapped into this more general framework. For example, for the Stigler model, where people simultaneously choose a optimal number of goods and start to search and then sort of maximize utility among those products. This framework can be mapped into the double index framework by just simply setting the reservation or search score for n-star goods to the highest possible utility, U upper bar, and U lower bar for setting it to U lower bar for the other products. As you can see, these are cases in which the search index thinks more kind of extreme versions, and so we definitely don't subsume these in terms of our implementation of it, because we are making parametric assumptions on the search score. But sort of if we could be, and this is one avenue that we're thinking for future research, be more flexible on the specification of the search score, we could potentially subsume some of these other search protocols as well. So I'm going to pause here to see if there are any additional questions on the overall model.
Giovanni, I have a question on the slide you just mentioned. So the separability between ranking R and things that consumer searches for, the X and X's, is that for convenience, for computation tractability?
Yeah, so exactly. So we kind of started from this, and we already have, as you will see, several parameters to identify. So yes, I would say, given the available data, this was the specification that we landed on. But to be honest, we haven't really pushed in the direction of more flexibility as much. I think that's definitely one of the things that we could do more exploration on. And for sure, sort of having kind of the interactions between X and R, or potentially even the fixed effects, sort of having that kind of interaction more, have more of those interactions, I think could potentially at least allow us to subsume additional search protocols beyond the Weitzman one, which is sort of the focus of at least this iteration of the model.
Yeah, I guess I was wondering, is it a computational constraint, or is it an identification constraint of these two?
Yeah, I think both are, both could be relevant. We haven't really thought about sort of the identification of each individual coefficient in these more flexible cases, but that would definitely be something to worry about.
Yeah, thanks.
Sure.
Giovanni, I was wondering if you'd thought about a model in which the search cost is also a function of some X's. So here the search cost only depends on R, but you could think it might also depend on star rating, things like that.
Yeah.
And maybe this gets back to what Yufeng was saying. I suspect that under a more flexible Weitzman model where you have that kind of search cost depending on X's, you might need a more flexible representation with interactions.
I think that's correct. I think the way to be consistent with that would be to have basically this F function have Rj, Xj. So basically that would require having an interaction term there, because then this is basically the term that comes from the search cost, right? And so whatever affects the search cost is going to show up in here. And so in general, having an interaction between R and X would be needed in that model for sure.
Giovanni, Raluca, go ahead.
Okay, quick question. So should we think about this search index as only taking in the expectation of this psi into account, or is there a way to also account for the variance of the
right? So
that people are searching for? Yeah.
Yes. So I think the if we wanted to have a that a specific hotel has we want to allow a specific hotel to have a different variance than another one, then I think we would basically have this, we would need this function f to have a subscript j, right? So we would basically need to have this function be specific to that hotel, right? Because the variance would also sort of the way the derivation is sort of, if we go back to the derivation, we'll see that sort of anything that has to do with the distribution, right, of the thing that you're searching over is going to affect this f term. If, for example, you have a model where your form x expectations about c, so let's think about this model here, your form x expectation about cu based on x, and this affects so not just the mean can be affected by x, but also the variance. Then similarly, I think this would actually be similar to what we were just talking about. This would also basically require an interaction between r and j inside the x function. So yeah, basically this particular specification effectively is just assuming, and this is sort of the why I have this IAD mean zero kind of term here, or specification here. The assumption is that the x is affecting the mean but not the variance.
Giovanni, can I ask you just on the generality of this? So it seems like that this kind of setting will necessarily restrict us to analyzing markets where I guess people mainly search for qualities, right? So kind of this vertical attribute that everyone values the same with the same sign. Do you have some thoughts on what it would take to make consumers search over the match values? I guess the more traditional way people thought about search in this context.
Yeah. So the reason we assume people know the match value is because, as we'll see in a second, that this allows us really to obtain these closed form solutions. So it is a trick that allows us really to speed up the optimization of rankings substantially. If this if we wanted to have people search over match value, I think we would generally, at least in general, lose the closed form solutions for the objects that we care about. And because basically what would happen here is that the search score and the utility score will, so the search score will not depend on epsilon ij anymore, right? This will be something that consumers are forming expectations over at that point. And we kind of lose this trick that I will show you in a second that really gives us some traction. I think it's definitely an assumption that we made for convenience. I think maybe the response that I would give is that the opposite assumption that is made sometimes in the literature, which is that consumer search over match value is also oftentimes made for different computational sort of reasons. And so ultimately that's, depending on the object that we have, we might go with one or the other.
But it looks to me that you could have both, right? You could have these epsilons that are observed to consumers before searching, and then you could have the second unobserved component that they are searching over. And so
you're saying two epsilons, basically, one that is known and one that is not known.
Right. So now there's epsilon number 2, which is hidden from you. That's going to be baked into the f of r function, right? Because your expectation is going to be different. But yeah, it looks like your double logit thing still works, but we can kind of discuss that later once you get there.
Right. I mean, so this is also a little bit in terms of like the way we're setting up the problem. So when I'm going to show you sort of consumer surplus, I'm going to think of this as the average surplus, the average surplus for the average consumer, right? So it's going to basically be an expectation over the epsilons, right? So I'm going to basically think of, given the set of hotels that you're facing, I'm going to think, what is the best way to rank these for the average consumer, where the average is taken over epsilon. Any, I would say, information that you have about the consumer, for example, demographics and things could be, I think, included in basically in the X's, right? So you could have interactions there that would allow the scores to be or the rankings to be personalized. We don't do this in this application because unfortunately we don't have a lot of or almost any information about the consumers or consumer demographics. But let me kind of show you the sort of how this trick plays out, and I'd be happy to hear if you have thoughts on sort of if this could be extended in any way.
Thank you.
Sure. All right. There are no more questions. Let me go ahead and sort of show how the model, this setup sort of allows us to gain traction in addressing our problem. So I'm going to, this is just I'm rewriting our two indices. I'm going to denote by delta S the average. Sorry, let me start here. The delta U is going to be basically the average utility, the mean utility for good J. I'm going to call delta S the baseline salience for product J before the F of R terms, or before adding any contribution or any bump that the in salience that the product gets from being ranked higher. We're going to assume that the epsilons are gamma distributed, which is standard assumption, and this is going to give us closed form solutions for choice probabilities and therefore for profits, as well as for consumer surplus. So first, for choice probabilities, we're leveraging a result from Choi et al. And this is an econometric paper that sort of shows that in spite of consumers searching in a complicated way with searching over products, in this kind of setting, the consumers ultimately choose a product, the product that maximizes what they call effective indices. So consumers ultimately end up solving a standard discrete choice problem where they end up choosing the product that maximizes this minimum of the two indices. So for each product, we can compute the effective index, the minimum of the utility and search score, and consumers eventually will choose the product that maximizes this object here across goods. In our specific setting, because of the, again, assumptions that we have made, we are able to essentially pull out the epsilon ij term because it shows up in both uj and sj, and therefore write it this way. We can basically take the minimum of the two average indices, and I'm going to call this delta v, and pull out the epsilon ij term. Then this, with the Gamble assumption, gives us this closed form solution for the choice probabilities, which I'm going to denote by qj, and I'm going to write these as a function of R just to highlight that the choice probabilities do depend on the rankings, where we get basically our standard logit formula for choice probabilities with the delta v's, so these terms here showing up inside the exponentials. And so the intuition for this result is very simple, which is that because choices are determined by delta v, so are determined by this minimum between the two average indices, two things need to happen for a product to have high market share. So a product has to be good, has to have high delta u, but it also has to have high delta s plus f. So it needs to be salient as well. If either of those are too low, so if the product is either not great or is not salient enough, then because of this minimum, the choice probability will be low, or the market share will be low. Second, we can get a closed form solution for the consumer surplus. So again, with our delta v definition here, we can show, and this is again in the paper, that the average surplus, so again, average across consumers, across epsilons really, takes this form here. So the first part over here to the right is, to the left, is the standard log sum formula for discrete logit model, where it would this would be the surplus that consumers would on average get if they had full information, and if the utilities that they got from the good was delta, the average utility they got from good J was delta JV. But this is not the full story. In our model, consumers are not fully informed. They search, and they sometimes get a higher utility than delta V, right? Because this is, again, the minimum of two things. Sometimes the utility that they're getting is higher than was sort of expected based on the search score. And so when this happens, consumers actually get a bump in their surplus, which is given by this second term on the right, where we're basically averaging, with weights given by the choice probabilities, these terms here, which we're calling potential of the different goods. So the potential of good J, which we're going to denote by phi J, is just simply the difference between delta U and delta S plus F. So it's basically, on average, how much better product is relative to sort of what it looked like based on the results page. It's basically a measure of the positive surprise that a consumer would get on average by consuming product J relative to sort of what the expectation was pre-search. And so again, the intuition is that while choices are based on delta V, the surplus doesn't depend just on delta V. It depends on delta U as well, because it actually depends on delta U. This is ultimately the utility that consumers get on average. And therefore, we need to account for these positive surprises in writing out the consumer surplus term. So this also gives us a closed form solution, which we can then use to optimize rankings. And so rankings are discrete. So obviously we have only sort of a finite number of possible combinations or possible rankings of the products. But just to build some intuition, we start from looking at this problem as if it was a continuous problem. So we're going to think of basically having a continuous ranking budget, which is given by this term here, J times J plus 1 divided by 2. And this is just 1 plus 2 plus 3 plus and so forth plus J. So it's just the total sum of the sum of numbers from 1 to capital J, the total number of sort of total ranking budget that is available to the platform. And we're going to ask the question, how do we allocate this ranking budget across different products in order to maximize the consumer surplus? And so here there's two parts. We are going to ask which products to rank. So we allow for the possibility that certain products might not even be ranked, so that some positions might be left empty. And also how to obviously rank the products that we do end up ranking. And so if we take derivatives of we take our closed form solution for consumer surplus and take derivative with respect to the position, the ranking of product J. So we're thinking of ranking as a higher ranking is a better position. So sort of this is the sign constraint that we're using, or the definition really that we're using, so that this f prime of our J is a positive number. This is the positive derivative. Then this derivative of consumer surplus with respect to our J is going to look like this. It's going to be equal to 0 if the product has a negative potential. So if the utility sort of if the product actually delivers a negative surprise, then there's no point in sort of promoting the product. It really shouldn't be in making the ranking of the product any better. And instead, if the potential of the good phi J is positive, then this is the formula that we get. So it looks a little bit complicated, but really the insight from this formula is pretty straightforward, and it is the following. So because Q and F prime are positive, the sign of this derivative is determined by the relative magnitude of this term in red, the potential for good J, and this term in blue, which is just the weighted sum of the potentials for the other products. And so this is basically saying that if product J has a high potential relative to its competitors, so if the red term is large relative to the blue term, this derivative will be positive, and so this is gonna be is gonna indicate that we should promote this product. We should give this product higher rank. And so this is a situation that we just label as diamond in the rough. It's a product that has a high potential, has the potential to deliver higher utility relative to what consumers expect ex ante. And so the platform should promote it in order to maximize consumer surplus. And the opposite situation is one where the red term is low relative to blue, so the potential for good J is low relative to its competitors, and therefore the product should be demoted. And so the best position should be given to different products. And this is kind of the situation that we label as clickbait. A product that doesn't really have a lot of potential, doesn't deliver a good utility relative to its baseline level of salience. So this kind of helps us build some intuition for sort of what the optimal algorithm should do. And just to make it a little bit more Chris,
Sorry, Giovanni.
Yep.
On the previous slide, I'm not sure I understand why you would get a 0. I mean, I understand mathematically, but sort of intuitively, if the ranking can affect the amount of surprise you experience, right? The company could change the position until you expect what you should expect or whatever. So you don't get a 0 here, because they can change the ranking, right, to affect the surprise level. So why would you ever get a 0, right?
Well, so what this is saying is basically that if we have a product that has a negative potential, right? So it's delivering already a utility that is below what you would expect.
I mean, for any position, for any ranking?
No. So this is at any given ranking, right? So this is, I think your intuition is correct. This is a derivative of consumer surplus at any given level, right? And so if at that level, the product delivers a negative the potential, then what this is saying is that you shouldn't promote it even further, because basically you're going to make it even more of a clickbait, right? You're going to make the salience even higher, and then consumers are going to have even more of a negative surprise down the road. And so I think your intuition is correct. If you then reduce, so this is saying you should demote the product, and by demoting, you're going to actually make the potential better for that product.
Giovanni, can I take another question about the generality here? So if I remember correctly, the Choi et al. Result was for sequential search, right? That assumes some sequentiality, and in the way you kind of set up the class of admissible search rules, you also explained it as sequential decisions. Does that mean that you assume away something like simultaneous search? Because that was one of your examples, so I'm a bit confused as to that, if that's allowed or not.
That's like I was trying to be clear about this, but let me reiterate: we're not subsuming any of those other models. So for this specification, we are committing to a Weitzman sequential model. That point was just to say this idea of characterizing the final choice as the result of two indices, one for search and one for utility, can be used to subsume other models. But doing that, I think, would require changing the estimation, and potentially would even lead to sort of different expressions for the things we care about, like consumer surplus and profit. So it was just a point about the double index framework, not about us subsuming that in this specific incarnation of the model.
I see. So the reason why you can optimize rankings here is because you do assume Weitzman and you use it to compute the consumer surplus, right? Because you'll need that to compute the f of r function and all of that stuff.
Right. So the Weitzman framework does give us, I think, these closed form solutions, which are really helpful.
Okay, thank you.
And so just to make the intuition a little bit crisper, I recently was at a conference in London, and so I was looking at hotels. And so let's consider these two hotels. One is a Marriott, and one is a more sort of boutique hotel called the Hoxton, which is actually where I ended up staying. And so let's assume that the Marriott is a little bit better in terms of utility. So it has a better utility than the Hoxton. Maybe it's bigger, has more amenities. But let's assume that because the Hoxton is a boutique hotel, it's a lot less salient on the product page, right? It's consumers, the baseline level of salience is a lot lower than it is for a big chain like the Marriott. And so what this our model would say is that even though the Marriott has a higher utility, it might be optimal for the platform to rank the Hoxton higher, because the Hoxton has a lower baseline level of search or of salience, and therefore a higher potential in the language that I used before. And so there's more to be gained by promoting the Hoxton, because again, this has the potential to deliver more of a positive surprise. And so this is an example of a situation where the model sort of delivered this nuanced intuition that ranking products by utility might not be necessarily the best thing to do. And I will show you that in the simulations, indeed, that's the case. We our approach sort of dominates in terms of consumer surplus an approach that simply ranks products by their utility levels. So we talked about the discrete problem just to build some intuition, but the continuous problem just to build some intuition, but obviously optimal rankings in practice are a discrete problem. And so in practice, what we do is the following. So given the primitives of the problem, so given basically the average levels of search index of the search score, the average utility, as well as this F function, these are all things that we're gonna estimate from the data, and I'll talk about it in a second. We can then compute the consumer surplus for any candidate rank. So now, with unlimited computational capabilities, we would just consider all possible rankings and pick the best one. But of course, this is a combinatorial problem that becomes, and so the number of possible rankings quickly becomes very, very large. And so what we propose is to instead use what we call the opk plus greedy algorithm, which does the following. We select a smaller number of products, capital K, let's say 3. That's what we do in the empirical application. We brute force maximize the consumer surplus from these 3 products, so from the first 3 positions. By brute force, I mean consider all possible combinations. And then we assign the remaining ranks greedily. So we just consider, the K+1 position and say, what is the best product to rank here? We find the one that maximizes the consumer surplus and we put it there, and then we move on to the next position and so forth. So it turns out that this requires a lot fewer function evaluations relative to this naive sort of fully brute force solution. And we are able to characterize sort of how far you are from the optimum if you do this as a function of K. And so the intuition here, and again, the paper makes it more formal, is that if the products that are ranked below position K are bought rarely enough, then this algorithm is sort of approximately optimal. So if it's the case that sort of the top positions get most of the purchases, which is sort of often the case, this algorithm will approach the optimum. We do basically similar derivations for revenue, for optimizing revenue or profits. I don't have too much time, so let me just sort of highlight that. I mean, the intuition here is actually quite straightforward. This derivative is going to be the derivative of profits with respect to the ranking for product J is going to depend on the relative magnitude, again, of 2 terms, which now are involve the margins. So this is the margin for product J, and this is the margin for the remaining products. And unsurprisingly, if the platform just cares about short-term profits, it should sort of promote products that have higher margins. All right, before I switch to the I'll show you some simulations and then the application. I'm going to pause to see if there are additional questions.
This may be outside of the scope of your model, but just curious to think about, does this just assume away any supply constraints? Like maybe the boutique hotels is ranked lower because if it's ranked at the top, then it's going to get sold out within 1 day. So it's like better to have it more down at the bottom of the page.
Right. Yes, I will say unfortunately, we don't really have that kind of information from the data, at least as far as I can tell. And so we're not, in practice, we're not able to incorporate that. But if I'm trying to think how the model sort of would change if the capacity constraints could be or one wanted to include those.
It could be a very negative surprise, I guess.
Right. It would be right. I mean, the utility, basically the utility would be essentially minus infinity if you cannot even book, right, the hotel. And so maybe that would be one way to incorporate this type of constraints, but it's not something we're doing in the current version.
There's a quick question from the audience from a couple of slides ago.
Yeah.
That you might refer to the empirical application. It's asking how you define the set of competitors for a product.
Right. So what we're doing is basically taking all the hotels. So we work at the impression level, and so this is a consumer choosing, looking for hotels in New York for a given time interval, and so we work with the hotels that were ranked on Expedia in practice. And the question is, we keep everything else fixed, we keep prices fixed, and we just ask what would be the best way to rearrange those hotels, potentially dropping some, so allowing for the possibility of not ranking all of them. But basically, we start from the set of hotels that were shown on Expedia, and that's the relevant set of hotels that we look at. All right, so in the last few minutes, let me first of all show you some simulations that kind of give a sense of the performance for of the algorithm. So here we look at a simple example with 5 products, because we want to be able to give a sense of how close to the optimum this OPTK plus greedy kind of algorithm gets. And so we want to have a small number of products so that we are actually able to do the brute force approach, compute the overall, the global optimum, and compare what we get with our approach to the global optimum. And so here we're actually reporting, we have several different parameter specification. This is the average over all these kind of different values for the delta S and delta U parameters. And we report the percentage of the total gain. So this is basically, we look at the consumer surplus achieved by the best possible ranking and compared to the consumer surplus achieved by the worst possible ranking, and ask, so this is the total amount of consumer surplus gains that can be achieved by choosing rankings. What fraction of those can we obtain, can we get via our algorithm? And so we do this for different values of K, which is our parameters, again, for basically how many positions we brute force. And we look at different ways of dealing with the remaining positions after K. So this, the greedy column is the one that I just basically described to you, but we also consider other options, which is just to rank the remaining positions randomly, or to even not rank any of the other hotels, just to focus on the first few. And so here you can see that K equals 3 kind of achieves, in the simulations at least, a very, basically almost all of the gains achievable from rankings, both when we look at consumer surplus and platform revenues. If we look at computation cost, because obviously this is the other big concern that we had, and our goal was to have something that would be quick. Again, we can do some combinatorics and sort of show that the number of function evaluations that are required for our approach is much lower than the fully brute force approach. Now this is for 25 goods, so a more kind of realistic setting. And we look at, for example, K equals 3, we obtain something that is in the range of 1/10 of a second. If we maybe want to be a little bit sort of less ambitious in terms of optimality, but be faster, we could pick K equals 2, and then we would be in the range of a few milliseconds. So this is basically runtime given the estimates of demand, the demand parameters, sort of this is the runtime to optimize rankings per impression. And so here, in practice, people talk about consumers dropping off and or losing interest in a product if the latency or the wait time is above like 1 millisecond or so. So where it might still be a little bit slow relative to industry standard, but it's still a fairly fast, fairly fast approach. And finally, I just want to show some of the sort of to showcase the value of having these closed form solutions. We compare performance. So we're looking at the percentage of consumer surplus gain, just like in a couple of tables ago, and runtimes in seconds. And we compare our approach, so this is our first column, to what the performance and the runtime would be if instead of using our closed form, you were to use simulation to approximate choice probabilities and consumer surplus. And so here we look at using 10 draws to simulate these probabilities, 100 draws and 1,000 draws. And as you can see, as we increase the number of draws, we the simulation approach becomes better, although still worse than the closed form solution. But the runtime, as expected, deteriorates very quickly. So here, even just with k equals 3, with 1,000 draws, the optimization would require more than 10 seconds compared to 100th of a second for the closed form approach. So this is sort of, again, one motivation for using the closed form solution, and also for some of the assumptions that we need to make in order to obtain those. In the last few minutes, let me talk about the empirical application. So this is a data set that has been used before, or Luca used this in her paper. So probably some of you already know this. I'm not going to spend too much time on the details, but it's basically a data set that is publicly available, in fact, from Kaggle on Expedia sessions. So it is a data set at the impression level. We see what the hotels that, again, specific consumers searching for hotels for a given time period in a given city saw. We see the position of the hotels, several hotel characteristics. We see the clicks that the person made, so the hotels that the person clicked on. We don't see the order of the clicks, but we see which hotels they clicked on. And we see the final purchase, if there was one. A key feature of this data set is that for half of the data, or for a portion of the data, the rankings are actually randomized. So Expedia was showing hotels in random order. And so this is really helpful because it allows us to estimate the position effects or the ranking effects sort of without worrying about endogeneity problems. So this is key to identifying what we call the F function, F of R. We're going to estimate our model on the random rankings data, get unbiased estimates of the utility parameters, the search parameters, as well as the F of R function, the position effects. And then we use the remaining part of the data, where Expedia is actually using its own algorithm, potentially sort of with endogenous rankings, for validation and counterfactuals. And so here, let me just quickly show you some results. From the estimation, again, this is the estimation on the random rankings data set. And we obtain sort of a set of coefficients for the search index as well as for the utility index. And just a few comments, the signs sort of broadly make sense. Hotels that have a higher star rating, higher review scores, that are chain hotels, and that are located in better areas. This is a location score that Expedia uses to assess how conveniently located a hotel is. They're all associated with higher search indices and utility indices. Price is negative in both cases. This coefficient is actually quite close to what actually Luca finds in her paper, so that reassured us. And promotion is positive, has a positive effect on both. I'm not showing you the position effects, but those are also sensible, sort of monotonic in the way that you would expect. And just quickly, some goodness of
Giovanni, can I ask you something on the previous slide? So does the difference in the coefficients tell us something about what consumers know and what they're searching over?
Yeah, so I think this is actually definitely one of the things we want to do some more work or investigation on, because for sure. So depending on, so in the simple example that we basically had before, right, where beta S, which is this, for example, this coefficient here, if you recall, where consumers are searching over what I was calling CU, beta S was defined as beta U plus gamma. So it was basically the combination of the utility that you get from, in this case, star rating, and the expectation that you form on CU based on that attribute, right? So basically, in this case, for example, the fact that star rating is higher, much higher, in fact, than the utility index, means that sort of you get some utility from star rating, but it's not a lot, because now remember, this is actually this is a coefficient that is fixing the CU, right? It's fixing the quality of the product, and so this is saying conditional on the quality. The star rating is not. I'm not getting a lot of utility from the star rating per se, But when I'm forming expectations, I use that star rating because I infer that the quality is going to be higher, right? And so this is one way to make sense of the differences. Now, we definitely have to kind of do a more systematic comparison. We're also in the process of, I should say, re-estimating the model in a slightly different way. So we're first going to do that and then sort of spend time on comparing the exact magnitudes of the coefficients. But I do think this would be an interesting thing to do, basically using these estimates to almost like test what the information structure is in the set. All right, so in terms of model fit, here I'm reporting the odds of clicking by position 1 through 10. I'm normalizing the first position to 1. So these are the odds relative to the top position. And as you can see, data is in blue and model is in orange. And we sort of broadly match the pattern in sample. So this is with the random rankings. Position 5 is weird. It's what's called an opaque offer. So it's basically a hotel where it's a position where consumers couldn't really see a lot of the details about the hotels. They just knew broadly the location, but not, for example, even the name of the hotel. So that's why it gets so many fewer, you know, a much smaller number of clicks. Out of sample, the fit is a little bit worse. So in particular, our model tends to overestimate clicks in lower positions, but broadly, sort of, we're not unhappy with the fit out of sample. Again, considering that this is a fit for a fully different ranking relative to the ranking that the data was estimated on. And so finally, the last thing I want to show you is a counterfactual. So we basically use our model, our estimated parameters, and the different algorithms that we talked about, and compare them in terms of consumer surplus, average consumer surplus, and revenue. And so this is these are some of the results in a nutshell. We normalize Expedia to 0, 0. So this is our baseline. This is the endogenous sort of the Expedia algorithm that we use as a benchmark. And in the blue dot here is the OPT3G consumer surplus. So this is our our proposed algorithm that targets consumer surplus. And as you would expect, it does better than other algorithms. And in particular, what I want to point out is that it does better than this diamond algorithm, which is the utility algorithm. So the utility algorithm, basically ranking hotels in decreasing order of utility, seems very sensible. But exactly like in the example that I gave before with Marriott and Hoxton, it need not be the best way to allocate the limited budget that the platform has, ranking budget that the platform has available. And so it actually this utility ranking performs worse, both in terms of utility, but also in terms of revenue relative to our OPT3G. The revenue optimal algorithm does much better in terms of revenue, as you would expect, but penalizes consumer surplus. So there does seem to be, at least on this part of the data, kind of a trade-off between consumer surplus and revenue maximization. And number of searches that consumers make across all of these algorithms is actually unchanged. So this is important because obviously we would be concerned if our algorithm delivered, you know, higher consumer surplus, but then required consumers to search a lot more. That could sort of go and reduce the overall benefit from the algorithm. But it's not the case in this case. I think I'm just in time, so I'm going to wrap up here. But I want to thank you all for joining. And I think I actually mentioned this already, including some of the next steps. One thing we definitely would love to do is try an implementation of this in the field, particularly given that it doesn't seem like we're too far from something that could be sort of computed relatively quickly. And so if anybody has any connections or knows of anyone interested in trying this out, of course, this would be a very welcome conversation to have. So thank you very much.
Thank you. I guess this Yeah, a round of applause. Thank you. So this concludes our sort of formal part of the talk. So anyone who wants to stick around for